Today we're going to be covering understanding regressions. This is going to be a couple of miscellaneous things about thinking about regressions, interpreting them, and just being a little bit more comfortable with them and some of the terminology that surrounds them. We're going to begin with a regression that we were talking about last class. We talked about last video, which was using time, how long a student takes on an exam, to predict how well they did on the exam. You'll recall that we had 4 variables predicting exam total. They were gender, if the student was female or not, their year, how much college they've been exposed to, how long they took on the exam in minutes, and how well they did on the homeworks, the homework total, between adding 3 and 4 together. So gender and year didn't matter, but homework total and time did. Both of those were statistically significant. So what I did is I reran the regression with both those just to keep our conversation a little simpler. That way we don't have a bunch of variables we don't really care about anyway. By the way, if it's not statistically significant, that means that you failed to reject the null hypothesis. And the null hypothesis, in all cases, for regression analysis, is that beta equals 0. Remember, the null hypothesis are things that doesn't really matter, right? Nothing really changes. This thing doesn't influence this other thing. This is a two-tailed test. Does it influence it by increasing it? Does it influence it by decreasing it? It's a two-tailed test. So that means the null hypothesis is that beta equals 0. It doesn't matter. So because we failed to reject the null hypothesis for those two, I just reran the regression, and now we have this regression, this estimated line, with time and homework, all the only things that matter. Now what I want to do for a moment, first of all, is to get a really good idea on that 0.74, that beta associated with time. Recall that the whole point of this story was a conversation I had with a friend. How long a student takes on the exam, does that matter for how well they did on the exam? That's the key point. That's the whole point of the conversation. That's the interesting bit, right? We're not surprised if people who did well on homework do better on the exam. What's interesting is if people take longer on the exam, do they do better on the exam? I wanted to find out if it was statistically significant, and I wanted to find out if it was practically significant. We call practical significance is that difference, is that level of influence, is that, in this case, coefficient, is that large enough to matter in any material sense? Like, if this coefficient was 0.0001, so if you take an additional minute on the exam, you'll get a tiny, tiny fraction of a point, and you would have to spend like 100 minutes or 1,000 minutes to even increase your exam score by 1. You can have a statistically significant result, but that would not be practical in any sense of the word, right? That would not be useful. However, this is not only statistically significant, this seems practically significant. Because if you take an additional minute on the exam, how much should your score increase? That's right, 0.7 points. Now, 0.7 points might not seem like that much because it's not even a full point. And I personally don't offer half points in my exam, so you can't even get a full point increase. But keep in mind, we're talking about only an additional minute of your effort. If you take an additional 10 minutes, how much would you expect your exam to increase? Well, to find that out, we would take 0.74 times 10, because that's our change in time, an additional 10 minutes, and that would equal 7.4 points. That's pretty big. You take an additional 10 minutes of your time to check over your work, to think carefully about some answers, and your final score for the exam goes up by almost a full letter grade. Rather than getting like an 85, you get a 92. Rather than getting a 60, you get a 67. That's pretty good. Now, again, I'm assuming that you're using that 10 minutes wisely. You can't just sit and stare for 10 minutes and expect to get a boost. But assuming you're using it productively, assuming you're checking your work and all that, it does seem to matter quite a bit. This idea, this breakdown, this ultimate takeaway from the analysis is what we call the punchline. And that term isn't official. It's one I picked up in grad school. It's one my dissertation advisor used a lot, and a lot of other people used a lot. But it's helpful. It's that key finding of your analysis. If X increases by 1, or 10, or 100, depending on what, I couldn't increase it by just 1 because 0.7 it's kind of awkward to say and to think about, but 7 makes a lot of sense why I multiplied it by 10. So when X increases, how much does Y increase? Right. If X increases by 1, for every additional person murdered, for every additional birth, for every additional dollar that people earn, or $10 or $100 or $1,000, for every additional whatever, how does my key variable, how does my dependent variable change? That's the ultimate takeaway that people want. If they could learn just one thing from any sort of analysis, that's what they want. How much does it matter? Does it matter? And how much does it matter? End of story. Right? That's the whole point. Granted, that's not technically always the whole point. Sometimes, as we've discussed, you are trying to predict actual values. Again, like if you're trying to figure out which house might be undervalued or which house would be a good fixer-upper for your, some sort of house flipping business, then you want to be able to put some data into a regression analysis and predict how much it should be based on size and location, and then say, oh, we can make a lot of money on that house if we fix it up. In other words, there's 2 ways to use a regression line. One is by predicting a particular value, and the other is by predicting how much the value changes. For example, I could use this equation to predict an exam score. I can see how long, for example, all my students might take on the exam. So an individual student might take on the exam. Like, let's imagine they take half an hour. And let's imagine, too, that they do very well on homework. So this, it seems small because it's only 0.097. But keep in mind that these are 2 homeworks. Each homework is 100 points. So this is out of 200. So it's a lot easier to get one more point here. If you think about 200 times that value on the end. So let's do that. Let's say this person did really well, 200. And then we can plug in these values. I could do this in a fancy way. I could do this in a non-fancy way. This is sort of the setup, right? Here's our intercept. Here's our other betas right here, beta for time, beta for homework, and then the actual values. If I really wanted to, I could use sum product, right? Multiply each of these values together, throw in a 1 there, so we maintain that 41.28. I could use sum product. Which, by the way, is technically what you're doing when you're doing a regression, is you have your intercept is really just treated as a coefficient for just a matrix of 1s, just a data of just 1s, like an 82.88. And if you don't believe me, of course, if you don't believe me, we could do the same thing. We do 42 plus that times that plus this times this. So imagine that according to this information I have about the student, I would expect them to get 82.88, right? They did super well on homeworks, but they didn't really take that much time on the exam. Maybe they're busy with something else. I don't know, right? I don't want to necessarily judge, but what I can do is I can see that roughly 83 is what I would expect from them. And then when I actually grade the exam, they get like a 70 or 60. I can be like, maybe something's going on with that student, and maybe I should ask them how they're doing, because it's way lower than what I would predict. Well, if it's a lot higher than what I would predict, maybe that student has really turned things around and they've come up with some really excellent study skills, and I would like to know what they are so that I can share them with people, or I could share them in the future with people who ask me, because I get this question a lot: how can I better prepare for your exams? Maybe I could use this as an example. And that's happened before, where I know some students did really well, and I was curious, what they did, and they told me that they didn't do well on the first exam, but then because they didn't do well, they started texting each other a lot and asking questions all the time throughout that unit in preparation for the exam, and then they did a lot better, right? They just really studied a lot more and regularly and daily rather than trying to cram, and that helped them a lot. I guess I can also use it too to detect cheating, at least suspicious cheating. That would be a pessimistic way to think about this analysis. All right. So that's one, is you can predict a score. The other one we talked about, you can predict a change in score. If you spend an additional 10 minutes, all of the things being equal, exam score increased by 10 times 0.74, or 7, roughly. Note, this intercept does not come into play at all. The other variable does not come into play at all. Doesn't, because mathematically they would cancel. The exam score before, exam score after. The only thing that's different then would be time before, time after. And so when you subtract one from the other, the intercepts cancel, the homeworks cancel, and the only thing that's left is change in time times 0.74. I did this in a previous video in more detail, to show you the algebra and the math behind it, and I talk about it as well in my notes under this section. So if you wanted to see that, but it's just very straightforward algebra. So I see no necessarily need to get into too much of it. I just wanted you to be aware that when you think about the change in score, or if you change just time, or if you add on a room to your house, or if you somehow move the house farther away, which is I think what I do in the notes. I'm not really sure why I decided to go with changing the miles from the city center rather than changing the square footage, which is a lot easier to do. But I did, so whatever. Maybe I was thinking in terms of someone trying to figure out what neighborhood they should live in, and they're like, well, if I go an additional 1.5 miles out from the city, then I will on average save $35,000 or something like that. So just be aware of how we can use this regression. Now, this regression line, though, interpreting it correctly, you do have to be paying careful attention to what your independent variables are, because the language that you use changes based on if we are talking about a regular number, like something like time, homework, that's easy enough, one additional point. But it's a very different story if we're talking in terms of percent, if our independent variable is a percent or our dependent variable is a percent. Let's imagine the unemployment rate is 6%, and then it increases to 9%. How much was that increase? Go ahead and think about it. I'll wait. If you said 3%, you are wrong. It was not a 3% increase. A 3% increase means you take 6% times 0.03 to get 0.18, and then you would add it to 6. Going from 6% to 6.18%, that's a 3% increase. Going from 6% to 9% is a 50% increase, because half of 6 is 3, 3 plus 6 is 9. So what do you say then? Do you have to calculate it every time? No. What you want to say is not a 3% increase. It is a 3 percentage point increase. The idea of a percentage point increase allows us to draw a distinction between talking about percents and just an incremental linear relationship of just increasing it without regards to necessarily where we started, that base value of where we started. Going from 6 to 9 is a 3 percentage point increase. This is also a 3 percentage point increase. This is a 50% increase, but this is not a 50% increase. It would have to go from, let's say, half of 20, 50%, so half of 20 is 10. 10 plus 20 is 30. It would have to go from 20% to 30% for these both to be a 50% increase. Similarly, if this went from 60 to 90, that's also a 50% increase, but is a 30 percentage point increase. So make sure that you're aware of that terminology. Percentage point is that incremental scale. It's not multiplicative, it's additive, it's incremental, like that. Now, why does this matter? Well, it matters because when we interpret these regression analyses, when we interpret these lines, if there's a percent somewhere in the regression, then we have to think in terms of percentage point. We can't think in terms of percent. There are ways to think in terms of percent if you change the equation in such a way, like if you're using a logarithmic scale, but we're not going to cover that. We're just sticking linear, so we only want to think in terms of percentage point. So here we have sales in thousands of dollars predicted by the number of rivals within a 20-mile radius. This is for a home improvement store. So number of rivals in a 20-mile radius and the percent of people in that 20-mile radius who own their own homes. That percent in the actual analysis will be indicated between a 0 and 1, like all percents are. Therefore, a 1 percentage point increase, not a 1% increase, but a 1 percentage point increase, or an increase of 0.01, multiplied by a coefficient of 300, would increase our sales by $3,000. Again, 3, but it's 1,000 because the sales are in thousands, and then dollars. You do always want to look at the actual data. Sometimes percents are indicated as just a number, like percent unemployment, 1, 2, 3, 8, 6, 9, whatever. Sometimes it is as a decimal, as I do here, 0.01. So you do always want to look at that raw data, and you do want to make that very clear in any analysis. You might be tempted then, so like what would it require to increase sales by 300,000? Well, you would have to have not a 100% increase in homeowners, but a 100 percentage point increase in homeowners, which is impossible unless you started at 0, unless nobody owned their home, and then you went to everybody owning their home. Seems unlikely. So again, one of the reasons why we want to think in terms of percentage point and versus percent and be cognizant of that difference is because they do have very different implications. Right? You can have 100% increase, that's easy. It's just a double, right? That happens a lot. It's a lot harder to have 100 percentage point increase. One way to do that is to go from 0 to 100. Right? Otherwise, you're outside of the bounds. Similarly, if we had a percent value as the dependent variable, then we would switch it up. So here's a hypothetical regression. It predicts customer satisfaction for pizza delivery. So lower prices, that's P. T is the time it takes for the delivery. I think I was thinking in terms of it was pounds of cheese. Whatever it is, it's a lot of cheese. So in this hypothetical regression, we would say that for every additional dollar that the pizza costs, this variable falls by 0.07. Because it's a percent, we would say 7 percentage points. Though again, we have to look at the actual data. Are we measuring percent? Is it just like, in the actual data? Are these the numbers? If these are the numbers, then this is a 0.07 increase, a 0.07 percentage point increase. However, if these are the numbers, then this would be to match it, 7 percentage point increase. So you do have to think about the data. That's why in all these analyses, in a lot of statistical analysis, they include the descriptive statistics, and that's something you're going to have to do for your paper, to kind of show you this is what everything's expressed in. This is the bounds of it. This is the median. This is the mean. This is the standard deviation. Just so it's really clear from anyone reading it what exactly you're working with, what exactly your data look like, or at least a better idea what your data looks like. Now, the other thing I want to draw your attention to is how weird it's set up, because the coefficient is 1.3. And that seems impossible because I just said, if it looks like this, right, which it does in this example, if it looks like this, then it can't be greater than 1. You can't have 130% people who are happy. That doesn't make any sense. How can it be 0.13? Well, the answer is because think about these variables, right? There are two big negative variables, price and time. Will it ever take a zero amount of time to deliver a pizza? No. It'll take maybe 10 minutes, typically. So immediately, you are subtracting off 0.5 from this 1.3. Is the price ever 0? No. Price might be like 8. I don't order that much pizza, maybe 8. Well, 8 times 7, 8 times 0.07 is 0.56, so you're also subtracting off 0.56. So we have a 0.5 or 0.56, you're subtracting off 1 right off the bat, over 1 right off the bat. And granted, there's some cheese, but you're not going to have like 10 pounds of cheese on a pizza. So within the boundaries of the data that we'll be looking at, you can see how you can get some seemingly impossible intercepts, because things have to decrease, right? They have to decrease by a certain minimum amount. And this also highlights one of the dangers when you think about regressions and you try to predict, well, what percent of people will be happy if we make the price like $5? It's like, well, you don't really have any data on something that extreme. What if we make it $1? It's like, that's something that's kind of outside the bounds of what we would consider reasonable. Like, things are going to have to taper off at those low prices. Or if we would take it delivered by drone, it takes only a minute. It's like, we never really did that before. So there are some natural bounds to regression analysis, to predicting what will happen. If you're way outside what things normally do, way outside the boundaries of the data you have, then you don't want to get too much into that. To take an extreme example, we talked about this too when we talked about predicting with time series. You can have year as your independent variable predicting sales. And that's a fine thing to do if you're trying to predict like next year's sales or maybe 2 years sales from now. But you can't use that to predict sales from 100 years from now. It doesn't make any sense, right? That's way outside the boundaries of what you're working with. You can also use regressions to predict dummy variables. So we can have a dummy variable trying to predict if someone will be employed when they graduate. Employed, question mark, 1 yes, 0 no. With that intercept, it's predicted by their GPA, so the better the GPA, it's positive. So better the GPA, the more likely they are to be employed. This is a statistical reality, though. Women are less likely to be in the labor force than men. So I put in, I just made up a number because this is just a hypothetical regression just to illustrate the point, 0.12. So if female, then you're less likely to be employed. What would it mean if we wanted to predict someone's employment? So a male with a 3.0 GPA, if we plug that in, where male means that the dummy variable is 0, GPA is that would be 0.6 plus 0.08 times 3, Well, 0.08 times 3 is 0.24. 0.24 plus 0.6 is 0.84. Well, how could that be? Because remember, we said dummy variables are either 0 or 1. This is not 0 nor 1. This is between it, but it's not 0 nor 1. It doesn't really make sense. How can that be possible? It's possible because, remember, we are predicting values. Predicted values can be between 0 and 1. We are predicting a dummy result. So the way to interpret this predicted value of 0.84 is to think in terms of percent chance. There is an 84% chance that this person will be employed after graduation. That means that when we interpret this coefficient, like say GPA, for every additional point in GPA that someone has, their chances of being employed increases by 8 percentage points. That would be our punchline. Adjusted for population is something to also consider when you're setting up your regression. You want to make sure that every variable that should be adjusted for population is adjusted for population. Do not ever put raw numbers into the regression, like the total number of police officers in a city should predict the total number of murders. On the surface, that's not inherently bad, but a lot of data out there is adjusted for population. And so you cannot, for example, do the total number of people, the total number of police officers predicting the number of murders per 100,000. Those are now completely different variables, and you'll get screwy results. In the data sets I provide you, for example, you see under country data, here we have child out all, that's what I want to look at. Child out all is the total number of children who are not in school. If you use this data for your paper or something, you want to make sure you adjust for population. Otherwise, you're going to get really screwy things. Consider the two countries, Israel and Egypt. They are right here. Israel has 17,230 children who are not in school, according to this data. Italy has about the same, 18,955. Does that mean that they are then in about the same boat as far as kids going to school, that they're about the same in terms of their ability for, to accommodate children to go to school? It seems so. But keep in mind, Israel has a population of about 6.7 million at the time this data was gathered. Italy has a population of 58 million, much larger. So while they seem like they're similar, when you consider their population, they're in completely different boats. The number of kids adjusted for population, kids that are out of school just for population, are going to be vastly different. So it's really important that you adjust for population when it's necessary. It's necessary that whatever the data you're looking at, whatever the variable you're considering, would it automatically increase, or would it be really likely to increase if you just add more people? If you add more people, then the total number of kids out of school will naturally increase. Because every family has a certain percent of the kids be out of school. If you have more people, then you're just, by the law of large numbers, simple multiplication, going to have more kids out of school. The total income of a country, or the size of the economy, the GDP, will naturally increase if you have more people. The total number of murders in a country will naturally increase if you have more people. However, the physical size of a country will not naturally increase. The unemployment rate, which is already adjusted for population, will not naturally increase. The population density the total population divided by the size will not naturally increase. So you really have to think carefully about the variable you're looking at. And if it's adjust for population, does it need to be adjust for population? To adjust for population, it's a simple process. It is the variable divided by the population. We can do this easily here in Excel. So here's child out all, here's our variable. Let's scroll, I'll keep it here. Here's Israel. I'm going to take it equal this value divided by their population. This is by the way, I have this population column. I'm not saying this is a good variable to use for your analysis. I'm saying this is a good variable to have to make adjustments for other variables. Now we have the total number of kids out of school per person. That's what you do when you adjust for population this way. If you take the variable divided by the population, well, you can divide anything by 1 and get the same result. So that means that whatever comes out is going to be a per person, per head, per capita, per individual, per one person. So this is why this value is so small. 0.002, 0.0003. It is so very small because it can obviously be 1, because that means that not only is every kid out of school, but every kid in the entire country, every person in the entire country is a child. It's like, by the way, you can't have like a murder rate be 0.5. You can't have half a murder for every person, because that means half the country is being murdered. I mean, I guess you could have that, but you don't want to be in that country. That would be bad. So, but you certainly can't have something that's like 2. You can't have 2 murders per person. That means not only is everyone being murdered, they're being murdered twice. Who's doing the murdering? It doesn't make sense. So you have to be aware of that. You have to make sure they make sense. That said, this is a very annoying variable. Right? This result, I should say. This result of kids per person, which is what we have here, is hard to interpret. So you have 0.002 kids, 256, what? It's weird. Let's see if we can fix that. And we can fix that with a scalar. A scalar is a constant value that you multiply the variable by in order to ease interpretation of the regression. So we can start by looking at our child out all. Now that we've adjusted for population, we made it child out per cap. Or per capita. Capita is, of course, Latin for head. We can do that for these other ones, too, just as long as we're doing that. But this is not easy. What would make this easier if it was maybe per 100,000? Per 100,000 people. How do we do that? Well, how do you turn per 1 to per 100? Per 100,000. You would just take the original value, multiply it by 100,000. And now we have something that's a lot easier. So for every 100,000 people in a country, 200 in Israel, 256 kids are out of school. 32 kids are out of school in Italy. Over 1,400 kids are out of school in Jamaica. And 1 kid is out of school in Japan. So note here with Jamaica versus Italy, it looked like it was maybe twice as bad. It's more than 10 times as bad. Now, I should mention that this is a very rough estimate because I'm assuming that the percent of children in every country is the same. That's obviously not the case. If you really wanted to drill down deeper, you would figure out the percent of a country that is kids. We have that actually over here. There it is. percent of the country that is between 0 and 4, percent of the country that's 5 to 9, percent of the country that's 10 to 14, percent of the country that's 15 to 19. If you really wanted to, you can figure out, we can add these two together. You know, that's percent, that's 5 to 14. That's school age, definitely school age. And so, you know, these two together, for example, looks like that's about 21.5 or 6 or something like that. And, you know, take that, you know, even though it's a percent, it's done as 10, so you'd have to move the decimal place over a couple of places to make it 0.2. And then you multiply that by the population to get the total number of kids, and then take the kids out divided by the total number of kids. You that you know, just as a side note, you could really drill down into that and make something even more accurate. But for our purposes, it's sufficient to show how vast the differences can be if we just simply do a really basic, sloppy, brute force adjust per population. So now we have a better idea. And we can talk in terms of for every additional kid per 100,000 that's out of school. You know, we put these values into the regression, we can get something that's more reasonable. We see this too with murder and non-negligent manslaughter per 100,000, right? It's per 100,000. Alabama has 7 murders in 2012 per 100,000 people. It doesn't mean that's 7 for the entire state, just 7 per 100,000 people. If it was per capita, if it was per person, then that would be, we would have to take 7.1 divided by 100,000, and you'll get this awkwardly annoying small number. We could also make it per 100 by dividing by 1,000. We could make it, what are the number of murders per million people? Well, to turn 100,000 into a million, you multiply it by 10. 71. That's pretty sure it's easy enough to do in your head, but still 71. 71 murders per million people. Rare events have scalars. We don't say births per person, we say births per 1,000. We don't say murders per person, we say murders per 100,000. Per 100,000, right? Crime data is typically done in per 100,000 for that reason, because it is thankfully rare. Let's imagine that you're going to run a regression with murder to predict unemployment. Before we get too far into that, let me show you the unemployment values. Note here the unemployment values are not bounded between 0 and 1. They are, no, this is 2012, this is after the financial crisis, and we could just harmonize it with what we've been talking about, make it that. Now it's percent unemployment, just so we're clear. And heck, if you really wanted to, we can just do that and throw in the percent value, and then maybe throw in a decimal. There we go. But again, this is an example of data that was presented in such a way that you do have to be aware of what the units are. Right? Is this 7 or is this 0.072? Is this 9 or is this 0.09? This is 0.09. This is just 9. I'll be able to zoom in a little easier. Let's put it in H. Sure. Okay, here's our results. So, not terribly surprising, statistically significant. Of course, we look at the p-values as normal. And it's not terribly surprising that this is a positive coefficient. As the murder rate increases, so does the unemployment rate. Of course, this is about 0.3 percentage points, that coefficient. What would happen? Here's the fun part. What would happen if I turned murder and non-negligent homicide manslaughter from 100 per 100,000, from per 100,000 to per a million? So I throw a scalar in, and the scalar is just multiplied by 10. What would happen to this coefficient? So we have unemployment rate, equals 0.06 roughly plus 0.00296 murders. If I make that, murders per million, what happens? Well, how do I turn something into, well, let me ask you this. What can you always multiply any number by and get the same result? Well, let's find out what happens. This is a simple thing to do. If I can find my murder rates. Here they are. We'll say it's per million here just to call it something. Now, how do I turn it to million? That's right, I multiply it by 10. Data analysis, regression. Same story, except now it's over here. And I want to compare the result. So I'm going to throw it all the way over here. Oh, that's okay if we overwrite a little bit of that. Who cares about that? There we go. Those confidence intervals I usually don't use. So we make it per million. I'll write that down here. This is the same. We're going to call this one B and this one A, I guess. But no, we added another decimal place. All right, it scooted everything down a bit. All right, we have 3 zeros, and before we had 2 zeros. Also note, our p-values did not change. It was 0.00278, and now it's 0.00278. For what it's worth too, our f-stats are exactly the same. All right. 9.921, 9.921. Everything is exactly the same, or all these other things. All right, R-squared is the same, about 6, everything is the same. The only thing that changed is the coefficient. Why did it go from here, 0.00296, to here, 0.000296? It's because the scalar doesn't really impact the statistical significance of the regression. It's just shifting the decimal place. And we can show this mathematically. What is the number that you can always multiply anything by and get the same result? That's right, 1. And we can express that 1 however we want. Let's express it as 10 over 10. Now, as mentioned, to go from in hundreds of thousands, the A version, to in millions, the B version, we multiplied by 10. And so when we did that, we converted, we'll say that we converted this from MA, which we'll say it's in 100,000s, right, to MB, which is in millions, or 1,000,000. Take that 10 multiplied by here, but we're still left with 1/10. That 1/10, I'm going to scoot it over here to put it next to the coefficient, and then multiply this coefficient by 1/10. Just moves the decimal place over 1. It's the same thing. It's the same thing, it's just been shifted around. That's what scalars are. If you multiply the variable by one number, then you will divide the coefficient by that same number. And as long as it's a constant, which a scalar is by definition, then nothing about the regression as far as statistical significance changes. The only thing that changes is your description of what the variable is and the coefficient, and those are always going to be in exactly proportion to one another. Let's do another example. Let's imagine we have sales in thousands of dollars equaling 30 plus 0.04 times the average income of, say, a state in thousands of dollars. So the sales in that state is predicted by income, average income in that state. Thus, if the average income is, say, I don't know, 50,000, that would be just 50. 50 times 0.04 is going to be 2, or $32,000 in sales. And how that way. Let's now convert this income from in thousands, or 50,000 50, to just ones. 50,000 is 50,000. Well, to convert thousands to ones, you would multiply. You would take that 50 value you have and multiply by 1,000 to get 50,000. Well, if you're multiplying income here by 1,000, then that means to adjust, you will divide. Note, if we take 0.00004 and we multiply it by 50,000, we still get 2. Just as when we took 0.04 times 50, we got 2. This is the same story. It just has a lot more zeros. And that's kind of the point. That's the point, because the regression hasn't changed at all just because we decided to throw in a scalar and multiply everything by. It's just a constant value. We're just shifting the decimal point. We're not really changing any sort of relationships or the degrees of those relationships. We're just calling it something different. What if we wanted to change the sales from, say, K to just ones? Well, it's the same story. I'll use S for sales, I for income, just to make my life a little easier. Give me some room. It's the same mathematical story, except now, rather than dividing these coefficients, because it's on the other side of the equal sign, we have to pull out our algebra. The sales are now just sales, not in thousands. And then we will take this 1,000 times 30, plus this 4 times 1,000. The income, as mentioned, is still in thousands. And now, if we want to express that, 50,000 income, well, 50,000 is 50. 50 times 40. 50 times 40 is 2,000, or 32,000, just what we had before. Again, scalars do not change the regression, not in any statistically significant way, not in terms of what the result should be. When you throw a scalar onto a regression, you change the coefficient, and you change it in proportion to how you change the variable you change with this. When you throw a scalar onto a variable, you change the corresponding coefficient. In the case of doing it to the dependent variable, you're going to change all the coefficients, including the intercept. If you change a independent variable, you're going to change only that variable's coefficient. And you always change it in proportion to how much you change the variable, just in the reverse way. This is useful. This is a useful thing to know, because remember, going back to the beginning of what we're talking today, beginning of the video, when we're talking about punchlines, it's nice to be able to have a useful number. 0.04, kind of an awkward number, honestly. But 40, that's a little better. So it's a nice thing to keep in mind that you can manipulate the data in a way that is purely aesthetic, and it helps you get a coefficient that leads to a more reasonable thing you can use for your punchline. Just like I did for the time and total data for predicting exams. Yeah, I said, oh, rather than saying every additional minute, I said the additional 10 minutes. Just as you make that adjustment for your punchline that I did, so I go from a 0.7 to a 7. You might make that adjustment here with the actual data, redefining what you're actually measuring, rather than mention in terms of income, in terms of thousands of dollars. You can just say in terms of just straight income, and that gives you can give you a better coefficient and makes it easier to interpret. And that's so much about what statistics is all about. That's so much of what running regressions is about. It's not merely about making sure that you got good data, that you specified the model correctly, that you don't have any multicollinearity or heteroscedasticity or autocorrelation, any of those other problems. It's not just about all that technical stuff. It's also about presenting these findings, because that coefficient, if it's statistically significant, that coefficient is the entire point of this regression analysis. It's not simply a matter of saying there's a correlation, these things are connected. It's also a matter of saying how much they are connected. How much does it increase when I increase the other thing? What are the costs? What are the benefits? Remember, regressions make a causal claim. They take correlation one step further by claiming a connection, and then they take it an additional one step further by saying how much that connection matters. What is the slope of the line? Just be aware of its limitations, right? There's lots of limitations. You can't go too far outside the data set. You can't take that age and height relationship and then project it out to 60 years old. That doesn't make any sense. There are all those assumptions built in, making sure the data is well gathered and all that stuff. But it's still a very powerful tool. Thanks.